Today, we're diving into the incredible story of a scientific discovery that completely shattered a fundamental rule of nature. It's a story about forbidden patterns, a hunt that spanned decades, and a final shocking answer that literally came from outer space. This is the story of quasicrystals.
Okay, so take a good look at this image. It's what's called an electron diffraction pattern, which is basically a snapshot of a material at the atomic level. Now, what you're seeing here, this perfect 10-fold symmetry, is something that for over 150 years, the laws of physics and chemistry said could not possibly exist in a crystal. It was like a square circle, a physical impossibility. So, how are we looking at it right now?
To really get why that pattern was so revolutionary, we first have to understand the rule that it broke. And this wasn't just some minor guideline, it was a cornerstone of crystallography. That's the science of how atoms pack together to make solids. This was a rule that had stood firm, completely unchallenged for well over a century.
So what exactly was in this rulebook? Well, for scientists studying solids, the world of atoms was supposed to be neat and tidy. It was thought to be governed by these incredibly strict laws of repetition. Let's break down what that really means.
The whole foundation was this idea of the periodic crystal. And the concept is actually pretty simple and elegant. Just think of wallpaper. You've one single pattern, right? And it just repeats over and over and over again, perfectly in every direction until it fills up the whole wall. That's how scientists believed all crystals were built. They had to be ordered and repeating, period.
And because of this perfect repetition, when scientists would analyze a crystal, they'd see a very specific, totally predictable signature. You can think of it as the crystal's unique geometric fingerprint. It was a direct result of that perfectly repeating atomic pattern. The rules were strict, they were predictable, and they were always verifiable.
And here is the absolute crucial point. Because of the basic math of how repeating patterns work, some shapes were just forbidden. They were off limits. I mean, think about tiling a floor. You can do it with the squares, no problem. Triangles, hexagons, sure. But just try tiling a floor with nothing but regular pentagons. You can't. You'll always get these awkward gaps. Well, the exact same principle applied to atoms in a crystal. Five-fold symmetry was forbidden. It wasn't just unlikely, it was a mathematical impossibility.
But what if the rulebook was just incomplete? What if there was some other way for atoms to be ordered, but without that endless, boring repetition of a single pattern? Well, this is where our story's protagonist comes in, a physicist who dared to imagine a new kind of matter that broke all the rules.
So, back in 1983, long before anyone had any physical proof, a physicist named Paul Steinhardt and his student Dov Levine were just playing around with these impossible ideas. And they came up with a theory for a completely new phase of matter, a solid where the atoms were arranged in a clear, predictable order, but in a pattern that never, ever repeated itself.
They even gave it a name, a quasi-crystal. It was a seriously mind-bending idea. I mean, it had the order of a crystal, but it didn't have the repetition. It was a perfect structure that was infinitely complex, one that never just settled into a simple repeating loop. And it allowed for all those forbidden symmetries, including that supposedly impossible fivefold.
This is a fantastic way to see the difference. Over on the left, you've got the world of traditional crystals. Periodic, predictable, kind of boring. But on the right, that's a 15th century Islamic garish tile pattern from Iran. Steinhardt would later help prove that this kind of pattern follows quasi-crystalline rules. It's incredibly complex, it's perfectly ordered, it follows clear geometric rules, but it doesn't just repeat a single simple block. It's just a beautiful ancient example of this radical new idea.
So, okay, Steinhardt and Levine had a beautiful theory. But a theory is just an idea on paper until you find proof in the real world. Now, the first lab-made quasicrystal was announced by another scientist, Dan Shechtman, just a year later in 1984. But Steinhardt was obsessed with an even bigger question. Could this impossible stuff actually exist out there in nature? And that question kicked off an epic, decades-long hunt. And this timeline really shows you just how long and hard this search was. After the theory in '83 and that first lab sample in '84, the whole field just exploded. But for Steinhardt, that wasn't enough. So in 1998, he launched a formal worldwide search for a natural one. And for more than 10 years, the search turned up absolutely nothing. Just dead end after dead end. Then, in 2009, a breakthrough came from the most unlikely place you could imagine. Get this, a collaborator over in Florence, Italy, was just digging through the university's old mineral collection. And there, in a dusty box that had been sitting in a drawer for years, was this tiny little rock, only a few millimeters across. Buried inside this totally unassuming specimen, their analysis revealed the impossible.
the telltale signature of a natural quasi-crystal.
But that just opened up a whole new mystery. Where on Earth did this tiny rock come from? Well, the museum's old records pointed to a remote stream, way out in the mountains of Russia's Kamchatka Peninsula. So in 2011, almost 30 years after he first dreamed up the theory, Paul Steinhardt, the theorist, was leading an expedition of geologists to one of the most remote places on the planet to dig through tons of clay, hunting for more samples.
And this is where the story takes its most incredible turn. The team actually found more grains of the material, and when they got them back to the lab and analyzed them, they uncovered an origin story that nobody, and I mean nobody, could have ever predicted.
The material wasn't from Earth. It just wasn't. The chemical composition, the isotopes, everything pointed to one single wild conclusion. The first natural quasicrystal ever discovered had an extraterrestrial origin. It had formed in space and then fallen to Earth inside a meteorite.
And you have got to hear this. The meteorite itself was 4.5 billion years old. It formed way back in the early solar nebula, before the Earth had even finished forming. So this brand new state of matter, this impossible pattern, was actually one of the oldest forms of solid matter in our entire solar system. How crazy is that?
And the discoveries just kept coming. I mean, that meteorite turned out to be a scientific treasure chest. They officially named the first quasicrystal icosahedrite. Then they found a second, totally different type they named digonite. And they even found a new regular crystal, which the International Mineralogical Association officially named Steinhardtite in his honor.
You know, this quote from his colleague Neil Turek just captures the whole spirit of this story. It's the story of a theorist who wasn't just happy with an elegant idea on a blackboard. He needed to know if it was real. He chased that idea from a patent office to a museum drawer, all the way to the frozen tundra of Siberia, all to prove that his theory mattered in the real world.
So what's the big takeaway here? The story of quasicrystals is just this powerful reminder that our understanding of the universe is always a work in progress. And it's not just a cool curiosity. This discovery has opened up whole new frontiers in materials science, leading to things like ultra-hard steels and non-stick coatings. It just goes to show you that even the most established scientific rules can be totally upended by a single stubborn question. And it really makes you wonder, what other impossible ideas are just waiting out there, maybe in a dusty old drawer or a tiny fragment of rock from space, ready to change our world?